The recording is live. Bluetooth is working. All right, welcome everyone to another week of General Chemistry 1, Chem 1A. Before we get into today's material, there's been two primary updates to the syllabus. Number one, based off of some student concerns, my office hours have changed. Instead of being Monday, Wednesdays, 5 p.m. to 6 p.m., they're now Monday, Wednesdays, 11 a.m. to 12 p.m. So right before class, instead of at the end of the day, when most of you would have already left after the lab. So my office hours will be Mondays and Wednesdays, 11 a.m. to 12 p.m. I'll be in room 859, which is actually just on this floor, all the way on the other building. You can also join a Zoom link, or you can contact me for an appointment, of course. The other update to the schedule primarily relates to the experiments. So at the very top, of course, today for lecture, we're doing nomenclature. In lab, we're doing experiment 0, aka lab stations. The big change is based off of a trial run. We will need 3 days for experiment 0. Experiment 0, the lab stations, previously was only for the first 2 days this week. But the other classes beta test suggests that we'll need all 3 days. It shouldn't really affect you, of course, because you will be coming for a wet lab and anyway. But of course, it just means that we'll have time in class to do some practice problems. Speaking of, everyone should now have a copy of a worksheet in front of them. It's landscape at the bottom right corner. It says in-class problem set. These documents are functionally identical to the workshops, but on days that we have wet labs, they will be called in-class problem sets. These problem sets are still your question banks that we will go through some questions in class. Some questions will be assigned as extra credit. All right. So straight off the bat, I'm going to announce it right now. The extra credit for this worksheet is page 5, page 3. So pages 3, 4, and 5. 2 different handouts. Take one of each. So I'll say right now, the extra credit for this worksheet is pages 3, 4, and 5. Again, I'll say it, on days that we have wet labs, we'll do these in-class problem sets. They serve the same purpose functionally as workshops. They're just allowing us to still get some practice. As always, these are our question banks for when you study for your exam, the most primary type of questions that I will ask. I've given everyone else another handout. We'll talk about that when we get to that relevant point, but I wanted to make that stuff clear. Before we get into today's lecture, do we have any questions? Okay. And let's get into it. Today, we are discovering our new chapter. I believe it's chapter 2 or 3. I don't remember exactly. But it's called Nomenclature. Nomenclature is affectionately referred to as naming. So the last couple of weeks, we've talked a lot about the history of chemistry. We've talked a lot about the context behind scientific research. And even last week, we covered the periodic table. We looked at certain elements. We understood what the trends were, the different particles. Today, we're going to be talking about nomenclature, aka naming chemical compounds. Now, the first thing we need to understand about naming is that we need to understand the concept of a chemical bond. A chemical bond can be defined as a bond, an attachment, we'll call it an attachment, between 2 atoms. There are 3 different types of chemical bonds. We have a single bond, which is comprised of 2 electrons. We have a double bond, which is comprised of 4 electrons. And finally, we have a triple bond, and that's comprised of 6 electrons. So notice the what's the word I'm looking for? Overlapping factors that they go up in multiples of 2. All right. There are three primary categories of chemical bonds. Number one is an ionic bond. An ionic bond can be described as the bond between a metal and a non-metal, here abbreviated as M and NM. Don't forget from your periodic tables, within the periodic table itself, it gives you the legend for what are metals and non-metals. That's one of the reasons why it's important to carry the periodic table to class every time. An ionic bond between a metal and a non-metal involves a direct transfer of electrons. After the ionic bond, we'll have what is known as a covalent bond. A covalent bond, in contrast to ionic, is between two non-metals. So Nm plus Nm. And instead of a direct transfer of electrons, covalent bond involves sharing of electrons. And then finally, we have what is known as a metallic bond, which is the bonding seen within a single metal. That W/in is my shorthand for within. You've probably seen my W/ before. Well, let me write it over here. W/ that stands for with. Now, the key difference between all three of these bonds, specifically as it relates to a metallic bond, is that metallic bond, it does not comprise of multiple metals. It's just the bonding seen within a single metal atom. This is what explains the malleable nature of most metals, such as an aluminum sheet or a zinc roof or something like that. The idea is that within the metal, it's bonded to each other, and it's known as metallic bonding. Throughout this class, we're going to see a lot of variations of ionic bonds and covalent bonds. We won't really go too much into the concept of a metallic bond. So let's first try to understand what exactly an ionic bond is and how it manifests. All right, so an ionic bond, as I have just described earlier, involves a direct transfer of electrons from the metal to the non-metal. An example of this is sodium chloride, NaCl, which a lot of us know conventionally as table salt. Between the sodium and the chlorine, we have a single bond, which is represented by that literally straight line. And within that single bond, there are two electrons, here just represented as these green dots in between the atoms. Now, I did say that an ionic bond involves the direct transfer of electrons from the metal to the non-metal. So what this means is that electrons are coming from both ends. So the question comes up, why do these atoms gain or lose electrons? This was a question posed on Wednesday's class. Is anyone brave enough to remind us, why do atoms gain or lose electrons in the first place? Yeah, I see a hand. They become like royalty. They want to look like noble gases. See, here's what happens. Oh, whoops, it froze again? It did freeze. Stop sharing. Okay, let me go back to sharing. 3, 2. No. Okay, that's weird. Stop sharing. Okay. All right, it just loaded out. Great. Let me try this once again. Go to application. Yes. Okay, that seems to have done it. Great. Okay, we're back. So, why do atoms gain or lose electrons? Ultimately, it's because they want to look like noble gases. Let's try to understand what happens in the case of sodium and chlorine. Now, sodium, hopefully we all have our periodic tables at the ready. Sodium, I don't like the gold. The gold doesn't pop that well. Sodium is in group 1, which means that it has one valence electron. Remember, valence is outermost. They're our first line of defense. Chlorine, on the other hand, is in group 7. So it involves 7 valence electrons. Notice I'm just drawing dots around the atom to represent electrons. Now, here's what happens. That sodium gives up an electron. Why do atoms give up electrons? They want to look like noble gases. Sodium will give up its electron. Where will that electron go? Well, it'll just go straight to the chlorine, because look at your periodic table. Look at where chlorine is. How many electrons does chlorine need to look like a noble gas? 1. So sodium is giving up 1 electron. It looks like a noble gas. Chlorine is taking that 1 electron and looking like a noble gas. Overall, what we see here is that sodium chlorine bond that's comprised of both of those electrons. Here's why this is so important. When they transfer electrons from the perspective of each atom, they have access to 8 electrons. The chlorine will be obvious. Surrounding the chlorine is 1, 2, 3, 4, 5, 6, 7, 8. Chlorine is happy. That's the octet rule. What about sodium? From the perspective of the sodium, sodium has access to 2 electrons. Wait, no, that's not 8. Why is sodium still happy with 2 electrons? Look at the periodic table. Yeah, I see a hand here. Is there another? You said neon or helium? Neon, exactly. Remember that sodium will have direct access to 2 electrons, which is identical to helium. We talked about this octet rule, where octet does say that it loves having 8 electrons, but 2 is also okay. You can also make the argument that since electrons orbit, like rings around a planet, that the sodium will eventually have access to all 8 electrons. All of this is there to tell us that an ionic bond is a direct transfer of electrons such that each atom ends up looking like royalty. All right. So where does this come from? What does this tell us? Well, don't forget that technically speaking, the sodium having lost an electron, remember it gave it up, it's a direct transfer, is positively charged. The chlorine having gained an electron will be negatively charged. It is these opposite charges that attract one another and cause an attraction and cause a bond between the two. What about a covalent bond? Well, I previously described this as having been between two nonmetals, Nm plus Nm. Let's take an example. Let's look at one of the classic examples of a gas, oxygen. Hopefully everyone in here recognizes oxygen as a gas. It's one of those gases that we breathe that exists in the Earth's atmosphere. The formula for oxygen is O2. Let's take a look at how it works. Each oxygen will come together. Oxygen is in group 6. So let me actually use a different label. Let me use X's for this oxygen on the right to make it clear. So we have two oxygens. They're in group 16. 16 has 6 valence electrons. We know that atoms are going to share electrons in an attempt to get to an octet. So we're going to share 1 electron from the oxygen on the left. We're going to share 1 electron from the oxygen on the right. The resulting structure looks something like this. Please notice that the electrons, we haven't said that they're being lost. They're just moving over for a more clear sharing capability. As of right now, from the perspective of the left oxygen, it has access to 1, 2, 3, 4, 5, 6, 7 electrons. So we're still not there yet at the octet. From the perspective of the right oxygen, same thing. 1, 2, 3, 4, 5, 6, 7. So we're not fully there at the octet rule just yet. So what are we going to do? We're going to share once again. The result of this ends up with 2 oxygen atoms. And in between them has a total of 4 electrons being shared. Remember, all I have done is simply move electrons to the center, making it clear that they're bonding. From the perspective of each oxygen atom, starting with the left, we see that it has access to 1, 2, 3, 4, 5, 6, 7, 8 electrons. From the perspective of the right oxygen, 1, 2, 3, 4, 5, 6, 7, 8 electrons. As a result, these oxygens now have a full octet via sharing. If we were to draw this out, we would say that between the oxygens, there is a double bond. Why a double bond? Well, remember, if a single bond is 2 electrons, then a double bond is 4 electrons. It's twice as much. There are those electrons still hanging out on those oxygen atoms. They're still there. These these electrons, the ones that are left over, are referred to as lone pairs. And the ones that are found within the bond themselves are known as bonded electrons. Ultimately, what matters is that number 8. It depends on each atom, which ones are going to be bonded, which ones are lone pairs. But as long as each of them has that 8, or some cases 2, everyone's happy. Let's try another one. Let's try N2. N is nitrogen. Finding it on your periodic table, it's actually to the left of the oxygen. It's in group 15. Nitrogen is in group 15. Group 15 has 5 valence electrons. First things first is we're going to share one. One electron comes from each nitrogen atom. We count from the perspective of each nitrogen. We have 1, 2, 3, 4, 5, 6. From the perspective of the other nitrogen, 1, 2, 3, 4, 5, 6. Okay, so we're not there just yet. We're getting closer. Each nitrogen had 5 to begin with. Now we're at 6. So what do? We share once again. All right, counting electrons, we see from the perspective of the left nitrogen 1, 2, 3, 4, 5, 6, 7. From the perspective of the right nitrogen 1, 2, 3, 4, 5, 6, 7. We're getting closer. We're not there just yet. We're going to share it once more. Now, this final drawing over here on the right should get us there. From the perspective of the left nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. Great. From the perspective of the right nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. Great. We represent this in the form nitrogen with a triple bond between them. And each nitrogen will have a lone pair left over. Again, what we see here is that some of the electrons will exist as lone pairs. Those are the ones that just hang out on the atoms. Some of them will exist as those bonded electrons. Ultimately, the reason why this happens is so that they can look like royalty. This simple idea, this simple illustration, explains the existence of diatomic elements. What are diatomic elements? Well, it's actually easier just to show you what they are. They are H2, N2, F2, O2, I2, Cl2, and Br2. Sometimes you might also see Hg2. These elements are what are known as diatoms, where the prefix di is represent 2. In other words, these elements do not exist as just one hydrogen, one nitrogen, one fluorine, one oxygen. They do not. They exist as diatoms. in this form where there are two of them bonded together. So if I ever refer to nitrogen in this class, I am literally saying N2. If I'm asking you about oxygen, I'm referring to O2. You are expected to know and memorize these diatomic elements. They're the only ones of its kind. Do we have any questions so far? Okay. Now that we have an understanding of ionic bonding and covalent bonding, I mentioned that we're not really going to cover metallic bonding. Now we can understand how to name chemicals. First up, naming ionic compounds. All right, so the first thing we're going to want to do is remember that ionic is between a metal and a non-metal. All right, the rules are, yeah, is there a question? Yes. So chlorine has 7, which is in group 17. Oxygen is in group 16, so it has 6 valence electrons. Okay. The rule is number 1, or rather the steps are number 1, the cation, aka the positive ion, is written first, aka on the left. The anion, the negative ion, is named second, aka on the right. Step number 2, the name of the cation remains unchanged. The suffix of the anion is replaced with "ide." So the cation is written first on the left, the anion is written second. There is no change to the cation's name, but the anion, the suffix, is replaced with "ide." Let's take an example of an compound we've seen so far, NaCl. All right, looking at your periodic table, remember I told you you are expected to know the first 20 elements kind of off the top of your head. It's okay if you haven't memorized them yet. That's why we have the periodic table. All right, we have here Na, which is sodium. How do we know that the cation, how do we know that the sodium is the cation? 2 reasons. Number 1, it's written on the left. That's probably the biggest hint. Number 2, if you look at the periodic table, sodium is in group 1, which means that its ideal charge is +1. That's what tells us that it'll be positive. And then we have Cl, which is chlorine. But of course, in the case of the anion, the suffix is replaced with "ide." How do we know that the chlorine was negative? Well, number 1, it's on the right in the formula. That's our big hint giveaway that it's negative. Second, again, if you look at the periodic table, chlorine is in group 17, which means its ideal charge is -1. For those of us who don't remember what I'm talking about with the ideal charge, that goes back to the table we covered last Wednesday. We talked about in groups, number of valence electrons and their ideal charge. Okay. That's how to get from formula to name. What if it were the other way around? What if I had given you the name first, such as lithium fluoride? Well, we know what the process looks like. We know that the cation is written on the left and its name is unchanged. So we know that lithium is going to be our cation. Looking at the periodic table, lithium is in group 1. That's how we know that its charge is going to be +1. Next up, we have fluoride. All right, how do we know that fluoride is the anion? Well, number 1, it's written second on the right. And number 2, its suffix has been replaced with "ide." Fluorine will be negative, and we know that it is in group 17, so it will be -1. But how does this get us to the formula? This is when we evoke something known as the crisscross method. The crisscross method literally involves bringing those numbers, not the charges, the numbers down in a crisscross manner. So the 1 from the lithium gets crisscrossed to the fluorine. The 1 from the fluorine gets crisscrossed to the lithium, such that the final formula is LiF, where there is a 1 after the lithium and the fluorine. However, we do follow general math rules. Anything that is not written is implied to be 1, so we simply write LiF. The crisscross method works pretty much perfectly. Say, for example, we had another situation. What if we had the compound magnesium chloride? All right, take a second for yourself. You should be able to quickly identify which one is the cation, which one is the anion. Magnesium's on the left, hence positive. Chloride's on the right, hence negative. So we would just write Mg plus and Cl minus. Am I correct? Are these the ideal charges for these atoms? No. Magnesium is in group 2. So what is magnesium's ideal charge? 2 plus. Remember, you can write it 2 plus or you can write it +2. They both mean the same thing. Chlorine is in group 17, so it is fine with the -1. What does the crisscross look like? We're going to bring down the 2 from the magnesium. We're going to bring down the 1 from the chlorine, such that the final formula is MgCl2. Remember, the 1 does get brought down. It is there, but we generally don't write the number 1. So the crisscross method works regardless of the specified charges, because you just need to bring the numbers down. What about in the case where they match the face value? So let's look at magnesium oxide. All right, we're hopefully getting a little better at this. So we should know that magnesium is in group 2, so it's 2 plus. Oxide, the ide is the replacement, so we know we're referring to ox as in oxygen. Oxygen is in group 16. Group 16's ideal charge is 2 minus. Here we have a case where the face values, the charges, both match. AKA, if we were to crisscross them, they become Mg2O2. Here's what happens when they're the same number. We reduce it such that the final answer is just MgO. In other words, if this was 3 to 3, it would go down to MgO. We want the lowest whole number ratio. I see a hand. Yes. Okay. Very good question. That comes back to the naming of ionic compounds. The names are unchanged for the cation, but for this anion, it's replaced with "ide." The di-tri stuff that you're talking about actually applies to covalent compounds. We're not there yet. We're just going to be there a couple minutes. So the big takeaway from that student's question is we do not need any di, tri, tetra business. Why? Because we know that magnesium is in group 2, so it's 2 plus. We know that chlorine is in group 7, so it's -1. So we are able to very quickly identify the formula without the name. Okay? There is another situation. What about if you are dealing with a transition metal and non-metal? All right. Let's remind ourselves what a transition metal is. Let's go back to the periodic table. The transition metal series is that blue block right there in the middle. Starts at group 3, goes all the way to group 12. If you recall, the one thing I told you about 3 to 12 is that the number of valence electrons are variable, and the ideal charge is also variable. So, if I were to ask you, tell me the name of Fe2O3, well, you would be able to tell me, okay, Supreet, I know that oxygen is in group 6, so it's 2 minus. But I don't know what the charge is of the iron because you cannot look at the transition metal series and just tell. For that blue block in the middle, it's variable. So what do we do in this case? We reverse crisscross. What does that mean? Well, looking at the iron and the oxygen, we have iron 2 and oxygen 3. Look what we're going to do. We're going to crisscross, but reverse. Remember earlier, what we did was we sent those face values down. We're swinging them up now so we know the charge. This is what tells us, of course, well, first and foremost, the 2 swings up to the oxygen. That makes sense. Oxygen is one of those elements that we can look at the periodic table and just tell. Question for the class. How did I know that it was negative? All the crisscross did was shoot the 2 up. How did I know that it was negative? I see a hand. Okay, that's one very good reason. What's the other reason? It is on the right side of the formula. Both of those logics make sense. Number one, you should already know by default that oxygen is negatively charged ideally. You also should be able to know that on the right side of the formula, it's negative. All right, so what does that tell us about the iron? Which brave soul wants to tell me the charge of the iron? I see a hand. Positively charged, what number? 3. Very good. So you flip, you reverse crisscross that 3 back up, and it is on you to remember if it's on the left, it's positive. How else would you know? Transition metals are always cations. All right, well, this just tells us what the charge is of the transition metal. This doesn't actually tell us how to name it. In theory, the naming is still the same. The cation goes first. I see a hand, I'll get to you in a second. The iron goes first, its name is unchanged. And then the anion goes second with its suffix replaced with "ide." But Sarah, it was Sarah who asked the question about the ditri, right? Sarah Lindquist? Yeah. So Sarah had a very good question earlier. Sarah asked, why don't we do something like di here to represent there are 2 chlorines? Well, remember, with just a little bit of inspection, not even 5 seconds, we can get the accurate formula that will tell us there are 2 chlorines. In other words, with just a very little bit of effort, you don't need the di. Well, you got to put in some effort to figure out the charge of the iron. So how do we make it clear to the reader what the charge of the iron is? What we do is we include a Roman numeral designation. The Roman numeral is written right after the transition metal and explicitly tells us the charge of the transition metal. If we read this name, we read this as iron 3 oxide. And remember, we don't need to specify the plus. Why? The iron is on the left. The iron is also a transition metal. What about the case where I say, give you the name first? What if I say, give me the formula for titanium 4 chloride? 2 handouts, 2 handouts. Titanium, that should be an M at the end. Titanium 4 chloride. All right, so take a second to look on the periodic table, try to find the chloride and the titanium. The Roman numeral is your big hint that titanium is in the transition metal block. For those of us who can't find it just yet, let me just quickly show you. Chloride is over here on the right. Titanium is in group 4. So here's what we know. We know that titanium is Ti. We know that chloride is Cl. We know from the table that chloride is -1. We know from the name that titanium is 4 plus. Remember, the Roman numeral tells us the charge of the transition metal. From here, we're then going to crisscross. That 4 goes down, that 1 goes down, such that our formula is TiCl4. Do we have any questions on this on so far? Yes. Oh, Nick, I'm so sorry about your hand. Yeah. Yes. Yes, that refers to, let me show you the labels right here. Whoops. All of those guys in yellow that are described as metals, either alkali, alkaline, transition, or other, are all positive. The non-metals over here in blue are almost all going to be negative. For all of the others, the metalloids, it just depends. It depends on the situation, depends on the case. And remember, lanthanides and actinides, we're not really going to talk about in this class. Very good question. Very good question. Okay. All right. That takes care of naming ionic compounds. That's between a metal and a non-metal. What about naming covalent compounds? That is between a non-metal and a non-metal. Okay, well, the rules are fairly similar. Number one, the cation is written first, then the anion. Number two, the name of the cation is unchanged. And the suffix of the anion is replaced with "ide." And then number three, which is the new adage, Greek prefixes are needed. Used to denote number. These include mono, di, tri, tetra, penta, hexa, and so forth. We all know our polygons: hexa, hepta, octo, nona, deca. Traditionally, mono is unused. Again, that comes back to the whole idea of we don't usually write one, because if you leave it by itself, it's implied to be one. So let's look at an example of this. Let's try to name N2O5. Okay. The cation is written first, then the anion. But wait a second, wait a second, wait a second. I'm looking at this compound and I see nitrogen and oxygen. Now, nitrogen is in group 5. Oxygen is in group 6. Didn't I teach you that the ideal charge of group 5 is -3 and the group 15 and 16, I apologize, forgetting the teens. And the ideal charge of oxygen is -2? How is it that I'm all of a sudden claiming that nitrogen is positive? Well, let's take a look at the charges. Now, What are we going to do? We're going to reverse crisscross. We're going to send stuff up. This becomes N5 plus and O2 minus. All I've done is reverse crisscross. The oxygen, well, the oxygen makes sense. The oxygen is in group 16. Its ideal charge is -2. The oxygen is fine. There's no question about it. What about the nitrogen, though? Nitrogen has 7 electrons. How many electrons will it have if it loses 5 electrons? 7 minus 5. 2. And do we have a noble gas with 2 electrons? Hell yes. So, is +5 the ideal charge? No. But it's a possible charge. So the fact that this isn't lining up with your taught expectations is fine. Because no matter what, they still both look like royalty. And that's what they want to look like. So the fact that the nitrogen is positive should not bother you. In fact, with just a little bit of effort, you can understand why. What's the name of this molecule then? All right, well, the name, well, we know the first one's going to be nitrogen. Nothing happens to the cation's name. And then we have oxide. All we're missing are those Greek prefixes. In front of the nitrogen, there will be a penta. Sorry, a di. There's 2 nitrogens. I'm so sorry. There's a 2 in front of the beside the nitrogen that tells us there are 2 nitrogens, hence dinitrogen. And in front of the oxide will be a penta. And this is where Sarah's suggestion of those di-tri stuff becomes really useful. Because of that ambiguity of the nitrogen and other compounds, it's sometimes difficult to know exactly how many there will be. So in covalence compounds, those Greek prefixes are needed. What about something like H2O, which we hopefully should all recognize as water? We don't even need to look at the charges. We can simply say this is dihydrogen oxide. And remember that mono is typically dropped. You could write dihydrogen monoxide. It would absolutely be correct. You just lose the couple seconds it took you to write the word mono. This is going from formula to name. What about name to formula? Sulfur hexafluoride. All right. The beauty of covalent compounds needing that mono di tri stuff is that everything you need to know is in the name. There is nothing written before the mono, so what's it assumed to be? Mono. Right in front of the fluoride is a hexa, which is 6. So I can very quickly say this is SF6. Yes. Hexa. So you do need to know your Greek prefixes. So we have di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octo for 8, nona, I believe, for 9, and deca for 10. Mono is 1, of course, but we typically just don't write this because it's implied to be 1. All right, we have one more special case. What about polyatomic ions? First and foremost, what is a polyatomic ion? A polyatomic ion is multiple atoms in one ion. For the purposes of naming, polyatomic ions will be treated as non-metals. So do we know what polyatomic ions you need to know? Well, I actually just handed out a handout about that. This is our first handout of polyatomic ions. Let me crop this. I'm going to tell you this right now. You are expected to memorize this document. Sorry about that. I will not be giving you this list as part of the exam booklet. You are expected to memorize them. I do recommend spending some quality time attempting to memorize this. You can use Quizlet, Anki, you can test each other, flashcards, whatever. But these are the polyatomic ions I expect you to know for Chem 1A. If you look through your textbook, there's bound to be hundreds more, but this is the only set I need you to know. And here's why memorizing it is so important. Let's look at the nitrite over here on the left. We have NO2 and NO3. Their names are different, only in one letter, nitrite and nitrate. The same thing can be said of SO3 and SO4, sulfite and sulfate. This usually presents an issue for people to memorize in the beginning because of that type of specificity. ClO2 is chlorite, ClO3 is chlorate. I'll be with you in a second, Sarah. You are expected to memorize all of these polyatomic ions and their name and their formula. Yes, Sarah. That's a perfectly fine logic for the subset I'm giving you. If you look at the complete list in the textbook, that logic won't be perfect. But for the list I'm expecting you to memorize, yes. What Sarah is pointing out is that the lower number is typically 8, and the larger number is typically 8. That actually appears here again, SO4 and SO3. That is absolutely true of this subset. But if you were to look at the entire list in the textbook, it may not be perfect. So let's try just 2 examples of this. We're actually going to go to the document, the problem set. We're going to do a couple from this first page. Is there anyone that does not have a copy of this problem set? Speak now or forever hold your peace. I can grab it for you. You have an extra? Anyone else? Okay. Just have an extra as well. Cool. All right. For those who came in late, I just want to say this out loud. On wet lab days, we don't have workshops. I will carry these in-class problem sets. They serve the same purpose. They're question banks. They're what we're going to work from professor guided questions. You're going to do some yourself, and some of them will be extra credit. I'll say it once again. The extra credit is pages 3, 4, and 5. The extra credit for this problem set is pages 3, 4, and 5. All right. Let's approach some of these problems. You all should have that polyatomics list nearby. Let's do some questions here. The question simply says, provide the molecular formula. So the compounds formula for the compounds that result below. The way you're supposed to read it is sort of like a diagonal. We want to know what formula it is when these two combine, when those, such, onward. Let's try the first row. We're dealing with CO3 plus. CO is a transition metal. It is cobalt. So I would have to specify the charge for you in such a case. We're looking for the combination, of CO3 plus and NO2 minus. What do? We're going to crisscross. We're going to say CO3 plus, NO2 minus. We're going to crisscross those face values. This becomes CO1, and we don't write the 1, and NO2, 3. But look at how this is written. This is really confusing to read. As written, the way how I've drawn this makes it look like I'm saying there is 1 nitrogen and 23 oxygens. That is wrong. So what do? We put a bracket. The bracket makes it clear we are saying there are 3 of that polyatomic ion. This is the molecular formula of this question. The question did not ask for the name, but I'm going to do it just for sakes of practice. We have here a metal, a transition metal, and a non-metal. So the name is going to go cation first, cobalt, no change. Then the non-metal, in this case, NO2 is nitrite. So you don't drop the suffix to "ide" because the name is set. What am I missing? All right, we don't need tri here because this is not a covalent compound. We have a metal and a non-metal, so this is ionic. Parentheses, Roman numerals. We were missing the Roman numerals that tells us the charge of the cobalt. Remember, the problem did not ask for the name, it just asked for the formula. I'm just going one step further just to give you guys some practice. All right, let's do the next one. We're going to do SO4 with the same cobalt. Maybe some of us are starting to visually see the crisscross. Hopefully I can just immediately write CO2, SO4, 3. Take a second and identify for yourself how I got these 2 and 3 numbers. Oh, excuse me. Where did the 2 come from? Where did the 3 come from? Just so we all see it, I'm going to show you. We have CO3 plus and SO4 2 minus. That 3 gets swung down crisscross. That 2 gets swung down crisscross. We put the SO4 in brackets because it's a complete polyatomic ion. Let's go a step further and try to name this now. What we have here is cobalt 3 sulfates. We do not need those Greek prefixes. This will not be dicobalt or trisulfate. That's unnecessary. Why? Because if we went the other way, we'd be able to say cobalt 3 plus, and when it's time for the exam, you would have memorized your polyatomic list, and you would have known that's 2 minus. Do we have any questions on one of these two questions we've done so far? Okay, I would like to now try the sodium and the NO2. So that fourth row from the top, this one right here. All right, notice I did not give you the charge of the sodium. Why is that? Sodium's not a transition metal, so it's on you to figure it out. Sodium is in group 1, which means its ideal charge is +1. We're going to combine Na plus and NO2 minus. This becomes NaNO2. What does crisscross tell us? Sodium is +1, NO2 is -1. Crisscross means this will just be a 1-to-1 ratio. The name of this compound is sodium nitrite. Am I missing anything in this name? Nope. All right, let's do a little bit of page 4. No, actually, yes, let's do a little bit of page 4. All right. We're going to do that very first cell. We have NH4 plus and P. All right, let's look for where P is on our periodic table. P is in group 15, so it is 3 minus. When we put these molecules together, NH4 plus and P3 minus, the crisscross leads us to NH4 in brackets with a 3 and then the phosphorus. All right. That's that formula right there. All right. Let's try the bottom cell right here, P3 minus and Br. All right. We know phosphorus. Phosphorus is in the group 15, so it's 3 minus. Bromine is in group 17, so it's -1. So here we have an immediate issue. Both of them are negative ideally. So how do we know which one's the cation, which one's the anion? Well, here's the trick. The atom with the lower group number takes the role of the cation, and the atom with the higher group number takes the role of the anion. Right? So phosphorus is in group 15. Bromine is in group 17. According to the trick, the lower group number takes the role of the cation, and the higher group number takes the role of the anion. So I want you all, I see a hand. Yeah. This only applies when both of them have an ideal charge of negative. You have to choose. This is the logic to help you choose. All right. So now here comes a question. Phosphorus needs to be our cation. Look at your periodic table. What does its charge need to be positively charged and look like a noble gas? Look at the number of electrons. Plus 5. When phosphorus loses 5 electrons, it ends up looking like neon. That is what tells us this is phosphorus 5 plus and bromine negative 1. Now that we have the charges in swing, crisscross tells us this will be PBr5. Let's take a second to also name this so we have some practice. This is going to be phosphorus pentabromide. The cells that are blacked out are impossible for you to answer. So don't attempt those, of course. All right, I just want to take a try from this problem down here. Problem 2, we're going to try these two right here. Okay. So identifying the elements is usually the easiest part. You should recognize there are two right here. We have Zn and SO4. SO4 is a polyatomic ion. And if you look at your periodic table, Zn is in the transition metal block. So with a very little bit of effort, we know this is going to be zinc, and we know this is going to be sulfate. Am I missing something? Yes. What am I missing? The Roman numerals to tell us the charge of the zinc. Remember, that blue block in the middle is variable. Unlike all the other groups, we cannot just look at it and tell. So we have to look at the formula. What do we notice about this formula? We should notice that these are in a 1-to-1 ratio. And since we know that sulfate is 2 minus, what must the zinc be? Someone say it louder. 2 plus. That's what tells us the Roman numeral will be zinc 2 sulfate. And let's try that last one right there, the NH4I. NH4 is a polyatomic ion. That is ammonium. The iodine is right beside it. Iodine is in group 17, so we know that it's the anion. This is iodide. Am I missing anything? Nope. The ammonium is a polyatomic ion, so I don't need Roman numerals. The iodide has been switched in, the ide. This is a covalent compound, so you do need the mono, the di, the tri, the tetra. But how much of each exists? Just one. So yes, you could technically write monoammonium, monoiodide. It would not be wrong, but conventionally we drop the mono. Does anyone have any questions? I saw your hand first. Yes. Because Roman numerals are only required for transition metals. Was there another hand I think I just saw going up? Yes, Mohammed. What was yours? Sorry, what did you say? So that is because sulfates is a polyatomic ion that has the 4 part of it already. So we do not need to specify or name the 4. Sulfate is SO4. Sarah, I think I saw your hand. I am not too picky on spelling like that. Sarah, you would probably be right. I would imagine that a lot of chemists out there would do that. For this, I'm going to try to teach you the exact rules. I'm okay if you wrote pentoxide, though. There's no real difference to me. So my rule about naming is if the typo changes the name, it's wrong. If the typo doesn't change the name, I'm okay with it. For example, I have seen some students on an exam in rushing, they write PINTA, Pinta. I would forgive this because I would know it's a typo. I'd know what you're trying to write. It would be fine. But if your typo here switches this to hepta, that's a pretty big typo that changes the number entirely. This would be wrong. So when it comes to typos, just remember small spelling mistakes won't get you, but if the spelling mistake is so severe it changes the name, it would be wrong. Any other questions? All right, great. We're going to end lecture for today. We're meeting in lab in building 600, room 604. I will see you all there at 1:30. See you in about 13 minutes.